So it's my pleasure to welcome John for his series of mini courses on Horocycle flow on Moduli space of translation synthesis.
So first off, I'd like to thank the organizers for giving me the opportunity to give this talk, this collection of talks. I thank him for providing the nice location, and you all for coming here. So what is the goal of my lectures? The goal of my lectures is to show that the Horocycle flow on the moduli space of translation surfaces exhibits some behaviors that the Horocycle flow in homogeneous spaces does not. So in Manfred's last lectures, he wrote down Ratner's measure classification theorem and mentioned that as a consequence of this, with additional extra work, you end up with an orbit classification statement and a genericity statement. So, for example, a one-parameter unipotent flow has the property that every point in a homogeneous space equidistributes for some measure. And also, all of these orbit closures are nice objects. And this is false for the Horocycle flow on the moduli space of translation surfaces. In particular, in strata, so don't worry if you don't understand the words I'm saying right now. Part of the point of the talk, of the course, which will be 5 talks, is to explain some of these terms. So in a particular stratum, say for the experts, H11, there's a residual set of points whose orbits under the Horocycle flow don't equidistribute for any measure. And also, there are points whose Horocycle orbit closures have fractional Hausdorff dimension. And moreover, there's an uncountable family of properly nested Horocycle orbit closures. So these are things that don't happen in the homogeneous setting. Okay, and that's the point of what I want to do with this course. In addition to introducing an object that we used in order to prove this, the so-called tremor of a surface whose horizontal flow is not uniquely ergodic. And then I'd also like to talk about some open questions on this. Okay, so I think that this is a nice topic to talk about in a mini course because it's, I think that there's a lot of questions that we have that we don't know how to answer, and it's not clear that there are massive difficulties to do it. I think we just need a lot of new ideas, and I think it's an interesting area for young people, for people to come into. Okay? So that's the goal. And then, so I want to briefly say what my 5 lectures are going to be. The first is an introduction to translation surfaces. A very abbreviated introduction to translation surfaces. Translation surfaces themselves could have a perfectly good 5-lecture mini course introduction to. And I'll just do that in the first lecture. So it'll be a little bit quick, it'll be a little bit imprecise at times. That's the goal of the first lecture. The goal of the second lecture is to talk about a particular construction of minimal but not uniquely ergodic flow on a translation surface that has been useful for many people to build interesting examples and as a place to prove results because they can be well understood. And this is 2 identical top copies of the same torus glued along a slit. And that's the goal of the second lecture. The third lecture is to introduce this object, tremors, that's one of the main points of the course, and to also prove the failure of Ratner's genericity theorem, kind of in 2 ways. Okay? The fourth lecture is to talk about weird orbit closures, to define something that's a weird Horocycle orbit closure, talk about the ideas to prove that it's actually a Horocycle orbit closure, and time permitting to talk about the fact that its Hausdorff dimension is fractional. It's strictly between 5/2 and 6. I'm sorry, it's greater than or equal to 5/2 and strictly less than 6. Okay? And then the last lecture will be a list of about 10 or so open problems. Okay? So that's the goal of this talk, of this collection of mini courses. Okay? Any questions on this at the time? Okay. Great. So now, what are we going to do in lecture 1? The goal of lecture 1 is to talk about translation surfaces. I want to introduce you to what they are and to think about them as 2 different objects. One is an object of itself, and one is an object that sits in the space of such objects. So a translation surface itself has a flow in every direction on it, a straight line flow, and I want to define this to you. But thought of as lying in a space of translation surfaces, that has an SL2R action on it. Now, if you once again go from the SL2R action on the space of translation surfaces it gives you a family of homeomorphisms between different translation surfaces. I want to discuss all of that in this lecture. I also want to briefly talk about coordinates on this space, so-called period coordinates. Okay, and the goal and the way that this lecture is structured is we'll do all of this in the case of tori, where hopefully everything is pretty clear, and then we'll move to translation surfaces, which maybe not everybody here has seen before. Who's seen translation surfaces before? Oh, most people have seen. Okay, so maybe this lecture will be boring for a lot of people, but hopefully you'll have patience with me. And please feel free to ask questions at any time. Okay? All right, so let's begin. So I want to talk about building some tori with some interesting kind of flat or translation metrics on it. So what I can do is I can start off with a rectangle, and I can identify the top sides together, and I can identify the horizontal sides, and I can identify the vertical sides together, and in this way I'll obtain a torus. Okay? Now, this kind of gives you a chart for this torus in to the plane, and you can lift dz or dx and dy from the plane up to this torus, and you can compute distances according to this, and you can get a path metric on this, and you get a flat metric on the torus. This gives you a very nice flat metric. I said the word translation at the beginning, so you could also think about this as being a chart, and then if I go off this end of the chart, where am I going to go back? I'm going to go back to here. So then in this case, the transition functions between these charts are going to be translations everywhere. Okay? Is everyone happy about this? Okay, I see some nodding, that's good. Okay, so this is a nice object, and if you look at the title of the slide, it's called Flows on the Torus. So from this chart, in the plane you could think about a line, say, going 45 degrees. Let's say you fix the axes, there's a line going into 45 degrees, and you can lift that line up to this torus, and you can kind of flow in 45 degrees, and you get a flow actually on the torus. Okay? So not only do you have a flow on the unit tangent bundle, but because directions are preserved by the transition functions between charts, that is translations preserve angles, I'm not saying anything fancy here, you actually get a flow on the torus itself. Everybody okay with this? And every direction has a flow. So your unit tangent bundle splits into S1's worth of flows that are taking place on the actual torus itself. Okay? This flow, okay, so I've got some slides of this flow. So let's look at a trajectory in a particular direction to make this precise. And that's, okay, sorry. I need to go backwards. Okay, good, I'm going back. Okay, so if you look at what these slides are, so the identification is when I come up the top is identified with the bottom, so then I get that next piece outwards. And the next piece that I haven't drawn would come out on this side and go up here. Okay, so this is a trajectory for a flow in a particular direction on the torus, and it gives you a well-defined flow on the torus itself. Everyone happy about this? Okay, so I picked a very nice starting torus, but there's a lot of different ways you could pick tori. So you could pick different parallelograms to give you a torus, but also you could play a different game where I can look at this chart sitting in the plane, and so now I'm going to introduce the SL2R action on translation surfaces, which is going to be a key idea, in the study of translation surfaces. So I could take this chart in the plane, I could take an element of SL2R, I could just act on this picture I see in the plane, and I get a different picture. And that's going to be a chart for probably a different translation surface. Okay? And there's more going on here. So I could think about how this element of SL2R acts projectively on the circle, right? And so different directions are going to be sent to different directions under this. So not only do I send this shape to a new shape, I send a direction to a new direction. Okay? And so that's the point of this next slide. Okay? So what I can do is I can do a Horocycle shear, for example, so I can apply a matrix, say, please let me know if this appears too. Can people see if I write here? Okay, so I can apply a matrix of the form 1 minus alpha 0, 1 to the picture I have here to turn my flow in a given direction, change it into being the vertical direction. I change my flat surface, and now I have these right? These lines get sent to the lines that you see below. Is everybody okay with that? So, oh, good. Okay, so that's kind of a nice picture. And so what's really going on here is that this map doesn't just give you a new translation surface from the old one, it's actually giving you a homeomorphism between these translation surfaces, right? We're sending a point a certain distance on this horizontal line to the same point a certain distance on the other horizontal line. I guess I'm doing it in the other direction, right? So you send this corner down to this corner, this point gets moved the same distance along, just as would be predicted by this matrix, and so forth, and you work that all out all the way across here. Is everyone okay with this? Okay. And so from this, and what this homeomorphism is going to do is it's going to be conjugating our two flows. Or really, it's a little more complicated by that. Do people know what an isomorphism between flows is? Who doesn't know what an isomorphism between flows is? Oh, this is great. Okay, good. Very excited. So definition. F on P, be a flow on X. On U. And F2, be a flow on Y, comma U. Then these are isomorphic. If there exists a phi from X to Y. Invertible. So that phi star of mu is equal to nu, and phi composed with f1 to the t is equal to f2 to the t composed with phi. Okay. So what's going on in this picture is that the flows, according to the blue lines on the top picture and the blue line in the bottom picture, are isomorphic to each other. This is a slight lie. You need a constant speed time change. If you go back to what I was saying before about the projective action of the matrix in SL2R on the circle, there's another piece of data you need to keep track of, which is how much those lines are expanded, right? And if you keep track of the speed at which these are expanded, then you get the appropriate conjugacy. So maybe as a good idea, it's often helpful to have kind of simple exercises to get a sense of whether you're understanding what's going on, or at least I find that helpful. So I'll now state two simple exercises. So exercise 1, which is going to be that the map 1S01 is an isomorphism of horizontal flows. And flows in different directions will be made isomorphic to to constant speed time changes of flows in other directions. So do people get what I mean by this statement? So this map gives you a homeomorphism between the translation surface, the torus you started with, and 1S01 applied to that torus, and that map can be taken as a phi, where it's going to be the isomorphism of your horizontal flows. And then exercise 2 is for e to the t, 0, 0, e to the minus t, what is isomorphic? To the speed 1. Horizontal flow. All right, so those are the two exercises. Any questions at this point? Okay, let's keep going. Okay, so now so there's an equivalence relation on these tori, right? I could take a torus and I could just kind of cut it. And I cut it along this diagonal, and then what I do is I take the bottom and I glue it to the bottom here. And I end up with this picture. Does everybody see how I got this picture? Okay, these two tori are equivalent, right? If I took a trajectory here, it would give me a trajectory here in kind of an obvious way. And if I took points, they give me points here, right? I know exactly where every point in here goes up here. These are the exact same tori. So this is an equivalence relation on tori, and from this we can start, and now we can start talking about the space of tori. Okay? But first I want to talk for a moment about renormalization. Sorry, I was getting a little bit ahead of myself. Okay, so there's a very important idea in translation surfaces that doesn't really show up that much in this mini course, but it's important enough I want to touch on it as much as I can. It will show up probably at a couple of moments, and this is the idea of renormalization. So this will also help us understand the equivalence relation I talked about. So I start off with these straight lines on a particular torus. This is exactly the same picture as I had at, I guess, the bottom of the slide a few slides ago. Everyone see this? And then I can cut in the way I cut before, and if you notice, this line is now going to meet this point here, and this is the picture you're going to get, with blue lines going to blue lines. Is everybody okay with that? And why stop? Let's keep cutting. Okay, so this is what we get. And then we want to cut one more time, and then I think we also are going to perform a flip operator. We're going to cut one more time, and we're going to end up with a picture like this. Okay? Okay, so let me just mention that throughout these steps, these three tori are all the same. And these are the same flows, and the flow in the given direction is actually the same. The isomorphism is the identity map. These are the same tori. Is everyone okay with this? This is a pretty ugly picture, so you could imagine that you want to change it a little bit, so you could apply the geodesic flow that I think showed up in Manfred's talks. Did people see the geodesic flow e to the t, 0, 0, e to the minus t? So what does that do? That contracts the vertical direction. And this kind of crazy side won't be as crazy big anymore. And similarly, this crazy side won't be as crazy vertical anymore. But we expand the horizontal instead, and we end up with a picture like this. So let me hit on the point that we've got the same torus we started with here, but here we've got a different torus. We've got a new torus because we've applied the geodesic flow to it. We've probably changed our metric in some way. Everybody okay with this? Okay. Yes?
But, I mean, applying e to the t to the minus t should give you the same torus, again, no matter how no matter how it represents the original torus, acting by the matrix will give me the same torus in the end.
No, it doesn't give you this. So this is a torus with a special geometric structure on it, and you've changed that geometric structure. It's got a metric, a specific metric, and you've changed that metric.
No, I started with a torus.
Mm-hmm.
These cutting operations you did gave me the same torus.
I agree 100%.
So that was literally metrically the same torus.
Correct, I agree 100%.
Apply e to the t to either of those representations, I will get different representations again.
This is a great point. So let's bring this up. This is actually one of my exercises that Lieber has kindly asked for me, 3, which is show cutting in SL2R commute. Show cutting and pasting. And the SL. Sorry, I misunderstood your question at first, or maybe comment. Okay, so
can I make a comment for this?
do you mind if I just say a few words and you see if you still want to say the comment after that?
Mm-hmm.
So this picture we have is a pretty nice torus, right? It's not crazy long, like the one we started with, it's a pretty nice torus. If I took the picture I started with and performed GT to it, it would look crazy long horizontal, okay? But those would still be the same tori, and I could just do the same scissor operations I did to this crazy horizontal tori to do that. And that's what I mean by these cutting and pasting operations in this SL2R action commuting. It doesn't matter which representation you perform SL2R to, the same operations are going to get you between them. It doesn't matter the order in which you do SL2R and scissor moves. Okay? So are people okay with what I mean by scissor moves? When I cut this along the diagonal and stacked it on top, that's a cutting and pasting move. And the SL2R is just the SL2R. And it doesn't matter if you cut first and then do SL2R or do SL2R first and then cut. Is that what your question was, Eeyore?
Yeah.
Okay, great. And do you?
And yeah, I still have my comments.
Yes, please.
Just to make the parallel with what Manfred said in his first talk, there was an SL2Z action and an SL2R action on the left and on the right in SL2R, and this is exactly what it is. Cut and pasting. So you're acting on the right with the cut and paste and left with the SL2R, but there's a left and a right action on the space of Torah. And this is just the same.
Okay, so thanks everybody. So now let's go back and kind of look at something. So if you notice, when we started with, this was a pretty dense kind of net of line segments here, right? It didn't take a very long horizontal trajectory to run into it. And what you see here is, at the end, you see a piece that's going kind of from bottom to top on a torus that doesn't have too big diameter. Okay? These two facts are related perfectly well, because if I look at a horizontal trajectory here and ask how long it takes to run into this blue line, and then I pull back that picture to my original one, the horizontal length is going to be contracted by e to the minus t. So it's going to get denser and denser. And so the idea behind renormalization, in terms of flows on translation surfaces, is to understand the flow on the translation surface. You instead try and understand often the geodesic flow of the translation surface you started with. And here you see that you've landed back in a compact set at a certain time, and that should give you some denseness result of trajectories. I'm not sure that makes sense. The topic of this is not renormalization, but this is a baby case of the idea of renormalization. Okay. So now at this point, I want to talk a little bit about the space of tori. Okay? So we have our nice equivalence relation on the space of tori, and we've got, and so then we can consider the space of these objects. So one thing to notice is that if I rotate my torus, I probably get a different torus with this. I'm not going to be able to cut it up and reassemble it to get a torus at a different angle, usually. There's some exceptional examples, like there's the square torus, and if you rotate it by pi over 2, you'll end up with the same torus again, right? And I think any torus rotated by pi gives you back the same torus. But if you rotate by a little bit, you're going to get a new torus. Is everybody okay with that? So this is different than the space of conformal structures on tori. So maybe in Manfred's talk, you talked about the hyperbolic plane modded out by PSL2Z. Did that show up in your talk? Okay, and you get this nice two-dimensional object, which is the conformal structures you can put on tori. Now rotations are conformal maps, and rotations change the tori in the sense I'm talking about, but they don't change the conformal structure on tori. But they do change these flat metrics on it. In particular, they'll change the direction a closed orbit is in. Changes the torus. Okay? All right, so you could think of this as being a circle bundle over Manfred space outside of orbifold points where it's something else. Okay, so that's one way to think about it, but I want to think about different coordinates on this space. I want to look at this picture, and I'm going to say, well, I could think of this torus as being the following thing. I could think of this as being this vector and this vector. And that's the data of this torus, right? It's this choice of these two vectors. So in this way, I can relate the torus to a point in R4. Or R2 cross R2 is probably a better way of thinking about it. It can be thought of as a point in R2 cross R2, which is just what is the vector that describes the sides. Now, of course, you should be complaining, how did I know I chose those? For example, if I wanted to describe a torus, how did I know I chose these sides and not these sides? Right? All right, so that would just be a different choice of charts in this space of translation surfaces, and the map between these would be an affine map. Okay, so this is an affine, so the space of, so this can be used to show that the space of tori is an affine, of translation tori, is an affine orbifold. Okay, people okay with that?
I don't understand.
Okay. Okay, so
What's the space? What's the identification? What are the objects?
okay, so the objects are these translation structures on tori. The identification between different ones of those are if you can cut one up, like in a finite number of times, you can cut it up and reassemble it and get the other one back. Okay, so that's the identification on this space. Okay, or that's the objects in this space and the equivalence relation on those objects.
Yeah.
Great. Okay, so now I want to put coordinates on those spaces, which is you can pick two of the sides in a representation, and you can think of those as being a pair of vectors, so a pair of elements of R2, and that's going to be the data. Okay? But of course, you could pick different sides using different scissor operations. For example, I could pick these two sides, or I could pick these two sides. Now, one of those pairs is the same, right? That one's the same as that one, but this one has been changed to be the sum of those two. Okay? Oh, it's okay for an orbifold to have different choices of coordinates, and the transition functions in this case will be affine. Thank you very much for your question, and did I manage to answer it?
Yes.
Okay, great. Thank you very much for it. I suspect other people are happy you asked it. Okay, I'm at least happy you asked it. Okay, so that's, okay, so now we've got a space of translation structures on tori, and we've got coordinates on these, which make them into an affine orbifold. Okay? All right? Now, these coordinates are good for other things, right? R4 has a natural volume form, right? You guys know how to compute volumes in R4, so I can get a local volume form on this orbifold. Moreover, this volume form is preserved by this affine changes of coordinates. Okay? Okay, so that's nice. We now have an affine orbifold with the volume form. Okay, good. And okay, so now the next thing is that this is a very non-compact space. This affine orbifold, it's very non-compact. I could take one of the tori that I've looked at before, say this one, and I could just scale it by 2 over and over and over again. And I'll be going off to infinity. Or I could scale it by 1/2 over and over and over again. And I could be going off to infinity. Okay? Now these tori aren't really different. And if I care about, say, the translation flow dynamics on them, they're really not going to be very different. So it makes sense to restrict our attention to unit area tori. Hopefully people are reasonably happy about that. And then it makes sense to not think about GL2, but think about SL2R acting on these. And SL2R will, since it preserves area on the plane, it's going to preserve the set of unit area translation structures on tori. Okay? Now, just 2 points to bring up. One point to bring up is the fact that my space still is not compact. You can take a sequence of tori which are having shorter and shorter simple closed curves on them, or that correspond to lattices that have shorter and shorter vectors in them. And this is going to leave and this is going to be going off to infinity in this space. Okay? And in fact, that's the only way of failure of compactness in the space of unit area tori. Now the next thing is I want to do ergodic theory on the space of. If you want to do ergodic theory on the space of unit area tori, it might be good to have a preserved measure. Right? That's a helpful thing for ergodic theory. And from our infinite measure, coming from our charts, just by viewing this as locally looking like R2 cross R2, you can get a finite measure on the space of unit area tori using a standard Koning construction. This unit area is going to be preserved by actions of SL2R. So now we have some kind of non-compact affine orbifold with a natural volume form on it that's preserved by SL2R. And then the last point to mention is that GT, the geodesic flow and the Horocycle flow, both act ergodically with respect to this volume form. And in this case, this is rather easy to prove, because any translation structure on the torus can be related to a parallelogram. Okay? You can pick a periodic direction, you can pick another periodic direction, and follow the pieces of one period along the other period till it closes up. You get a picture of a parallelogram. Okay? And any two parallelograms of area 1 can be sent to each other by elements of SL2R. Okay? So SL2R acts transitively on the space of translation structures on tori, and therefore it acts ergodically. And so the geodesic flow is ergodic, and also the horocycle flow is ergodic. Is everyone happy at this point?
Just about orientation.
What?
You have no problems with orientation?
Okay. Yeah. Are there any? I don't think so. So in particular, if you rotate a torus by pi, it's the same torus. You change, you do the negative flow, but it's the same torus. Does that maybe answer your question?
Maybe.
Are there any other questions at this point? Okay. Who's been lost so much that they don't even have a question to ask? Can't even ask a question. Okay, so I guess I'm boring people, sorry. Okay, so but let's just briefly summarize. So we have introduced a space of translation structures on tori. We've talked about how there's an SL2R action on that space, and moreover, it gives you a homeomorphism that changes the flows on one torus to the flow on the image torus. There's a space of these objects, translation structures on tori. It's an orbifold, and it has charts on it that come from the sides. If you restrict yourself to area 1 objects of this form, then there's a volume form on it, which has area that's a finite volume, which I haven't said any words on why that's true, just take it for faith that that's true. And the geodesic flow and the horocycle flow act ergodically with respect to this. Yes?
So what about other ergodic properties, like being RID in the geodesic case and mixing of all orders in the horocycle case? Do those survive in this setting?
I believe the Bernoulli. Oh, yeah. So in particular, the Bernoulli, I think it's actually Bernoulli, and that also generalizes to the space of translation surfaces, and it's exponentially mixing. Mixing roll orders follows because it's Bernoulli.
But a horocycle is that mixing of all orders?
I don't know, off the top of my head, I don't know. Okay?
Since you are talking only about tori, aren't we looking...
I'm about to talk about translation surfaces in a moment. So but at this point, I'm only talking about tori.
about SL2R mod SL2Z?
Yes.
So why are you saying orbifold and not manifold?
Because I think it's an orbifold.
No, it's a quotient of a Lie group, so by discrete subgroups.
Well, the torsion contains torsion.
But
So there's
it's not, I'm not looking at SL2R mod SL2Z mod K. I'm not taking a double quotient. I'm just taking a
As a topological space, SL2R modulo SL2Z if you think about it like that, then it's a manifold. But when you think of it as the circle bundle over moduli space, then we do see the singularity at the orbifold points of upper half plane modulo SL2Z. And I think this is what is happening.
Okay. But in any case, the spaces I'm talking about will be on the nose orbifolds. Okay. So, any other questions? Great. Okay. So now I want to move on to, are there any other questions? Let's actually, okay, great. So now I want to talk about translation surfaces. So what's going to be a translation surface? It's going to be a finite union of polygons in the plane, which has the following remarkable properties. Sides come in pairs that are parallel and of equal length. The translation, and what I do is I identify these pairs, and in this way I end up with a surface. I will essentially always be thinking of the case where you end up with a connected object, right? You could take two parallelograms that we've seen already, you could identify the sides, you get a disconnected surface. But we're going to be considering the connected case pretty much in general, and this is going to be a translation surface. Okay? Why is it called translations? Because the parallel pairs are going to be identified by translations. Right? So your transition functions between charts are translations. Slight lie there, that I'll get to in a moment. Okay, so that's what it is. Now, as is often the case, a picture is worth 1,000 words. So I'm drawing you one such picture. So here's going to be this is a collection of polygons in the plane, in particular one. It has sides that come in parallel pairs, so for example, this one and this one, that are equal length. This one and this one, this one and this one, this one and this one. So there's 8 total sides, but there's 4 total pairs. Okay. And you can identify them, and so you get a surface, and when you go off this side, you move over to here by a translation. The transition function between the charts are translations. Okay? And from this, you can get a flat metric on this space also. And so it turns out that this is a genus 2 object with a flat metric. Now there's a lie going on here, which is that I've got a funny point at the corner. So if you look at this point at the corner, by the identification, that's the same as this point. And that's the same as this point, and that's the same as this point, so it's the same as this point, this point. All of the vertices are identified in this picture. If there's 8 vertices that are all identified, and if you look and you go around it, you see that this has a cone angle of 6 pi. Okay? So there's going to be a special chart that you need to have, which is for this kind of funky point, this singular point, where your transition function is going to be where your map is going to be a root, right? That's going to be your map from your surface to the plane. Everybody okay with that? Okay, so let's. Okay. Okay, so what is a translation structure on a manifold more generally? It's a special metric on the manifold on a surface minus a finite number of points, so that the transition functions on the surface minus the finite number of points are all given by translations, the transition functions between charts. Moreover, at this finite number of points, they're all cone angles that are of angle integer multiple of 2 pi. That's the definition of a translation surface. And by triangulating things, you can always get the polygons I talked about before. But okay. Okay, so now we want to go through the kind of checklist we talked about before and get a family and start talking about the flows on these translation surfaces, the SL2R action on these translation surfaces, the moduli space of these translations, the space of these translation surfaces, and we want to talk about all of this. Everyone happy about this? Great. And so first off, let's talk about how they have a straight line flow in every direction. Okay, so here's kind of an interesting picture. So I'm drawing now 2 polygons in the plane, and I want to identify, so I identify parallel sides. So the parallel sides within the polygons are identified, except 2 special ones. The blue line, which I've decorated with this square, is identified over here to this blue line decorated by the square, and the red line decorated with the triangle is identified to this red line decorated with the triangle, but otherwise the sides are identified within the polygons. Maybe that's to avoid getting a disconnected translation surface. Everyone okay with this? And so I can pick a direction to flow in, and I can start moving. So I pick this direction, say, and I hit here, and so I'll now come out over there. Oh, I guess I'll come out over there, right? Because the translation vector that takes this to here is that. So, right? And now I'm hitting the red part at top, so I'll be coming out over here. Right? Everybody okay with that? So you've got now, so from the plane, just as before, because translations preserve angles, you have a flow on your surface in every direction. Now, one moment of caution, your flow trajectories that go into the singular points, which don't have a chart where the transition functions are translations for it, the flow here is not well defined. Okay? So this is going to be a measurable flow, but it's no longer going to be a flow defined at every point. Okay? But what are you losing? You only have a finite number of these kind of vertices, and so you lose an infinite ray, an infinite half line in that direction from each of these vertices. Everybody okay with that? Now, we're sitting in a 2-dimensional space, and I'm removing a finite number of lines from this 2-dimensional space, so still this is a perfectly good, well-defined flow, Lebesgue almost everywhere. This flow also preserves Lebesgue measure, just as in the case of the torus. So this is a nice object. And I've got a one parameter family of these flows on these translation surfaces, just as I did in the case of the torus, but now it's not defined at every point, but it's defined almost everywhere. Okay. So I also want to go back to my original picture and talk about the equivalence relation in this case, and see one example here. So I've cut along this diagonal, and I chose to glue this side on top of this side, and I ended up with this picture, right? So this line is this line. Oh, wait a second. This line is this line, and this line. This line and this line are the lines I cut, are the two sides of the line I cut on. And the place I glued is this line, which was this line and this line. Everybody okay with that? And I could have glued at lots of other points. I could have glued along this and gotten a different picture, but these are all the same. So if you go back to the idea that it's a finite set of polygons in the plane with certain pairings, you identify two of these if you can make a finite number of cuts and gluings to reassemble the picture you had before in the new picture. And let me just stress, you're not allowed to rotate. Rotation is forbidden. That's what these objects are. Okay, so now I want to talk again about these coordinates I had. So here, you have these four vectors. You have 8 total sides, but they come in pairs. So there's 4 sides that actually matter. And you can keep, these are 4 vectors in R2. So picking the sides you're talking about, you could identify your surface with R2, with a point in R2 to the 4th, right? For the data of these 4 vectors. All right. And so locally, you can move around in the space of translation surfaces by perturbing sides. So if you go back to my picture here, what am I doing between these 2 pictures? I'm taking this black side and I'm stretching it out and changing its direction slightly. Right? And I can do that completely freely and keep all of the other sides the same length. Take it on faith that all of these other sides are exactly the same length. And in this way, I can end up moving around locally and getting new translation surfaces. Let me mention that I've drawn kind of a funky picture here. The red lines could be stacked on top of each other, and so the red line can't be moved freely, or similarly with the blue line. But if I stack the pictures on top of each other in either way, then whatever is left of the red and blue line could be moved freely. So this picture was chosen in kind of an awkward way, but all of the other sides can be moved freely. Somebody had a question.
Not sure if it makes sense. The origin is somewhere, and I'm referring to the coordinates that you mentioned a moment ago. Each side is a vector, but if I just give you the vectors, how do you know how to assemble them into a polygon?
That's a perfectly great point. This raised its ugly/beautiful head earlier when we talked about the space of tori. Here's one collection of 4 sides. So imagine this side, this side, this side, and this side are one collection of 4 sides. But I also have this side, this side, this side, and this side. I think I picked 4 different sides. And those are different collections of 4 sides. 3 of them overlap, but one of them is different, right? I've replaced this side at the bottom by this side, which is some kind of combination of these 3 sides. Okay?
But I'm suspecting that you're not
answering your question.
Answering my question. My
Okay,
question was just regarding, say, the left presentation.
Mm-hmm.
I give you 4 vectors,
Mm-hmm.
but in the picture they are situated in the plane somewhere, and
Mm-hmm.
so
You've already made that choice.
But you say it's coordinates, so I need to give you 4 vectors, and you need to build me a surface, right?
Yeah. So
how do
okay.
you do it from the 4
So
vectors?
what's going on here is that you need a triangulation of the surface, and so you've picked out.
Just a different version of this question.
Yeah.
So I think for every polygon, suppose I have a polygon.
Mm-hmm.
I don't have, the polygon has, among all the sides, k of them are sitting on my polygon.
Mm-hmm.
You could say I have k parameters that perturb the size of the polygon,
And
but
you
the polygon has to be closed. So I lose 2 parameters from the fact that
Oh,
I
yeah,
follow
yeah.
the side, right?
Yeah.
So I think that is the question here, right?
Is that
These
your
are not
question?
independent coordinates. You have to subtract, these are
Yes.
not independent coordinates.
Let me help trying to, there might be another question.
Mhm.
Namely, John was emphasizing that these are local coordinates. If I just tell you, oh, there's 5 sides and the lengths are 1i, 2 plus 2i, and a list of 5 complex numbers or vectors in the plane, you're not going to be able to reconstruct the polygon. You have to say where those sides lie on the surface. And there's really, in fact, a countable choice of polygons that with a given length data you can assemble from them. It's really only local coordinates in that space.
I see, I see. So you're not, so you're actually giving me the surface, and
Yes.
I see. Okay, okay, I misunderstood.
Okay, so thanks, Martin. Yeah.
Oh, yeah, so spicy, so locally, you only get one real number per side, not two? I mean,
No, you get 2. You get a complex number or an R2. So if you look at this picture I've drawn
minus
here,
one number.
that's supposed to be suggestive. The black line has changed in kind of a significant way from the black line you had here. And you could choose to rotate it, and the whole thing would rotate with it.
Okay, so we get one complex numbers for every pair of identified sides,
If
minus
you
one,
chose it correctly.
like minus one complex number for each, minus one complex number for each polygon.
And the count is slightly off. I think he's going to do the correct count.
No, I'm not
The
gonna
sides
do-
are independent at some point.
Yeah, I'm not going to do the correct count.
I can tell you the correct count at the end. So this count is maybe correct. Well, it depends on the identification. This count is not. It depends on the number of singularities that you're create by the whole gluing process, and depending on that, your count is correct or not. I can elaborate.
You are maybe to answer your question, there is no -1, because the sides appear in pairs. For each side, you will get the same side with the opposite orientation, so things will automatically flow.
Okay, so these are coordinates. So let's take it on faith that these are local coordinates, and that this gives the space of translation structures the structure of an affine orbifold. Okay? And let's now make some remarks about it. So there's some important data going on in these objects. So one thing is the genus of the surface we end up with. So it turns out that this is a genus 2 surface. But there's another piece of important data, which is how many singular points there are on the surface itself. So you can represent it in different ways, in different number of polygons. I'm not asking about vertices. I'm asking you to identify the different vertices together. You look at those where you don't have an angle of 2 pi around them after you do the identification, and you count those. Okay? That's another worthwhile piece of data. So there's a difference. So here it turns out that there's 2 singular points, and in the picture I did here, it turns out there's only 1 singular point, even though they're both genus 2 surfaces. And these are kind of combinatorially different translation surfaces. Okay? There's one more piece of relevant data, which is for each of these cone points, what is the cone angle about them? Okay? So you can think of that data as being the cone point with the cone point, the collection of angles about the cone points, and with multiplicity gives you a piece of data, and you call the translation surfaces with that piece of data a stratum of translation surfaces. Because a family of translation surfaces are stratified according to this data. So that's why it's called a stratum. Everybody happy about that? Right? So in this case, it turns out that you have 2 cone points with angle 4 pi each, and in this case, you have 1 cone point of angle 6 pi. It turns out that they're both genus 2 surfaces. Right? So that's a stratum of translation surfaces.
So stratification is just a fancy way of saying the space is divided into subsets.
Yeah, exactly. Okay. All right, so now let's talk about the space of translation surfaces. So we have these local coordinates. In this case, it looks like it's going to be r2 to the 6th, but really it's r2 to the 5th, because what I should do is I should plot red on top of red here, and then you lose 1 pair of my sides, right? And I'll have the other sides, and blue will still remain, so I'll have r2 to the 5th worth of parameters. And this gives me a local volume form on the space, which will be preserved by my transitions between different choices of sides. My affine transitions between my different choices of coordinates will preserve this volume form. As before, this is a very non-compact space. I could keep dilating this object or keep contracting this object down, and I would leave all compact sets in this space. So it's natural to restrict ourselves to area 1 translation surfaces. Everyone happy with that? This space also has a volume form on it that's inherited by a coning construction from the volume form we had before on the space of these translation surfaces with any area, without that area constraint. Oh, I'm restricting my attention right now to a stratum, to a particular stratum. Right? All right. Now SL2R acts on this space, and in this way it preserves this nice volume form, which I will call Maser-Veach measure. So on a given stratum, you look at the set of area 1 translation surfaces on that stratum, and you get this volume form that came from this coning construction, and we call this the Maser-Veach volume, or Maser-Veach measure. Is everyone okay with that? I'm going to use that term in subsequent lectures. SL2R preserves this volume form, and now here is a fact that I'm not going to prove. The action of both the geodesic and horocycle flows is ergodic with respect to this volume form. Now you get the horocycle flow once you get the ergodicity of the geodesic flow, but that's an actual theorem you have to prove, that the geodesic flow is ergodic. Because the SL2R action on this space is no longer transitive. So this isn't an easy proof. Now in this set of area 1 translation surfaces in a given stratum, this is still a non-compact space, and the non-compactness is given by shrinking aside. That's the way you leave compact sets. So you can look at a given set, you can look at the set of area 1 translation surfaces so that the distance between any of the 2 cone points is greater than or equal to epsilon, and that's going to be a compact set for all epsilons bigger than 0, and the union of these will give you the entire stratum of translation surfaces. And in this sense, that's describing how you leave compact sets in this space. There's a similar version of this if you're talking about the moduli space of Riemann surfaces. So these are special metrics on surfaces. But you could forget about the spectral metric and just think about the Riemann surface, which is looking at all of the conformally equivalent metrics and calling them the same. And that has a similar way of leaving compact sets, but that's given by the existence of short closed curves. Let's ignore that fact. But just to kind of complete a picture. Yes?
Is there ergodicity an outcome of mixing, similarly to the torus case, or is it not the case?
So the proof that's easiest for me would use Rosy-Veach induction, and you'd be pretty close to a proof of mixing, I think.
In reality,
but I think you could stop before you got mixing. So this is one particular proof I know, and you could stop before you got mixing, but I suspect you could work a little bit harder and get mixing pretty quickly afterwards.
So mixing holds?
Yes, mixing holds. And it's actually, I think, a theorem of Veach that it's Bernoulli. Okay. But I'm lying to you. Though geodesic flow is not actually necessarily ergodic on a given stratum, it turns out that the strata don't need to be connected. The connected components have been classified. There's at most 3 of them in a given 3 connected components in any given stratum, and so you should restrict your attention to connected components of strata. I will avoid that discussion for the remainder of this course. Essentially, everything in this course will be at the stratum where you have 2 cone points, both of whose angle is 4 pi. So here's an example of such a surface here in front of us. And in this case, that stratum is connected. Okay, and the rest of our course will be essentially talking about this one particular stratum. Right, so that's kind of a fun thing. Okay, so we've talked about the space of surfaces. We've talked that there's a preserved volume form. This is a non-compact orbifold with an affine structure on it. And then the last thing to mention is that SL2R acts the same way as it did before by just, you look at this picture, you multiply this picture by a matrix, that's a well-defined thing, it's just sitting in the plane, you get a new translation surface, and those are identified. Similarly, this is giving you an action on, this matrix gives you an action on projective space, and it'll send the flows in one direction to a flow in a different direction, possibly at a different speed, because because it might stretch or contract that line. And this is the space of translation surfaces. Okay. Yeah. Oh yeah. Right.
Earlier it was a probability measure, right? When I said to R minus to Z. Here it's is it a finite measure or?
And up to scale, yes, it's always a finite measure, and up to scaling you can choose it to be a probability measure. People do think about the right scaling and compute the volume forms. That's an area of research that this course will not talk about at all. Yes?
So you're interchangeably calling two different things the space of translation surfaces.
Mm-hmm.
So is the space of translation surfaces the space of surfaces I get by gluing, or the space of pairs where it's a surface and a direction? One is kind of a circle over the other, but
So the gluings, you're not allowed to move so gluings are always only translations allowed. The gluing is not, you're not allowed to rotate when you
no,
glue.
that is it. What I mean is that sometimes you talk about translation first as just as a surface.
Mm-hmm.
So you say a surface together with a direction for the flow.
Oh, you can think of the north.
Exactly, there's a non-canonical isomorphism between the two. Or I say picking the north to be your, or the upward direction to be your favorite direction.
In our case, it's going to be east. East will be the favorite direction because we want to do the Horocycle flow, but you pick east. So yeah. Okay. I think this is probably as good of a time as any to stop and now formally now is strictly question time. People want to ask any questions?
Perhaps we should thank you first for the lecture. And then any questions?
Yes.
Do you have a good reference for basics such as what you talked about this lecture?
Yeah, I think Alex Wright's notes are very good, except any issues with the coordinates. And then there, I think you'd want to maybe go to section 2 of Bainbridge, Smiley, Weiss's paper. Okay, so, but I think Alex Wright's notes are great for everything except the coordinates. Yeah.
Regarding the measure that you mentioned, so you gave us local coordinates.
Mm-hmm.
So if I look at this picture and I think of, I choose a vector for each pair,
Mm-hmm.
I'm allowed to kind of slightly change it, right? Wiggle it,
Mm-hmm.
and maintain the fact that I see a closed polygon, say, and this would be a nearby surface, right? Now, the measure that you referred to is just the Lebesgue measure on the corresponding Euclidean space that I mentioned.
Yeah.
So the thing that I'm thinking of is if you have two singular points that are kind of approaching each other and the limit they are
So you're leaving
then
compact sets in this space.
Yeah.
So first thing to notice is you're leaving compact sets
right,
in your strata.
accumulating on another strata, right?
Yeah.
So the question is, why is the areas summable in some sense? I mean, I'm trying to think, why is it, can you see the finiteness of the measure?
I think the proof of finiteness of the measure is theorem.
Is what?
I think you need a theorem to prove this.
I tend to agree with John that it's a theorem to prove the finiteness, but when two singularities approach, that's not a big issue. You could almost include it in the space and extend the class there. Take a triangulation that is local around the two singularities approaching, and include the relative distance between the two in your coordinate system. Since that coordinate goes to 0, it's not going to harm you. The measure is not going to blow up there. It's other points where you go to the boundary of moduli space, and there the area, well, tends to go to infinity, and to control that, that's the theorem.
Are there other questions about this? Yeah?
I guess a different way of asking this question, asking this kind of question. So we have a map from the space of translation surfaces to moduli space, which is stately control. So this is
a crazy map, let's just say. This is a crazy map.
Well, yeah. So this is not something which you say, okay, this is a compact. This is kind of a fiber bundle with compact fibers, and I can.
No.
I
It's
see.
not a fiber bundle.
It's a positive, it loses dimension, the moduli space is dimension 3g minus 3. That space is dimension, well, depends on the number of cone points.
Yeah.
So that map is depending on the number of singularities,
Yeah.
surjective or not.
Yeah.
And even if it's surjective, it's not a fibration, so fiber dimensions might
Oh, I
might
see.
jump up, over some lower dimensional loci in the base.
Oh, I see. So
And I think that's already enough for John to qualify that map as a crazy map.
yeah.
Yeah. So maybe just one thing to mention for people, the question going on here is I'm picking a Riemann surface with a special metric on it. It's not just a Riemann surface, but I could forget that metric. So any two Riemann surfaces, so if I have two metrics which are the same by some bizarre conformal map between them, they're the same Riemann surface, okay? And I want the mark that just forgets this additional structure and only remembers the Riemann surface. And the claim is that's a crazy map. And so in particular, this, your space can't be viewed as a fiber bundle over moduli space.
So what are the three connected components in the structure?
There's at most three. They're classified by whether or not hyperelliptic, and then there's another invariant called spin. So you can have even or odd spin, and then you could be hyperelliptic or not hyperelliptic. So those are the three options. So you could be hyperelliptic and not hyperelliptic, and odd spin or not hyperelliptic and even spin are the largest collection of possible differences. And sometimes you only have two of them, and sometimes you only have one of them. Did that answer your question, or did I dodge your question entirely?
So yeah, I need to figure out what is hyperelliptic and
So hyperelliptic is pretty clear. Is pretty easy. There's going to be on this entire stratum a map that sends a homomorphism for each surface that's going to vary continuously in this space that sends that surface to itself. That's a hyperelliptic involution. Okay, and then the spin invariant is another object.
okay, thanks.
So what you're saying is when you have only one connected component,
Mm-hmm.
it's hyperelliptic?
No, that's not necessarily true.
Oh.
But when you have multiple connected components, they can be classified by this three pieces of data where some of these are empty, possibly. Did that answer your question? And Vincent, did I say it correctly? Yeah. Okay, good. Any other questions about this? But forget about the issue of connected components for the remainder of the mini course, unless you care to think about it on your own, but it doesn't show up in the mini course. It's just the fact that the geodesic flow isn't necessarily ergodic on strata. That was a lie, and I wanted to point out that lie to people.